Hello, so thanks to the MIDL organisers for having me. I'm Thomas Joyce, and I'm going to be talking about this work I did with Agis and Sotos on deep multi-class segmentation without ground truth labels. So as an introduction, as we've seen at this conference, we have a lot of successes when we have a large amount of medical image data with accompanying paired labels. In that situation, we're able to train very powerful models that do very well, but it's interesting to remember that we're getting our ground truth labels from humans, and they aren't learning by looking at thousands of pairs of input data and associated ground truth. They're doing something else. They're doing something somehow more high level. So here we have a picture of a radiologist doing something high level, and the question is, what sort of thing are they doing? How are they able to do this when at the moment we need loads and loads of paired data, and apparently they can look at one or two examples in a very high level way and generalize very effectively. So a little bit more motivation. Imagine I come to you with an alien modality that you've never seen, and let's call it XZ. So this is I've made it up, so I know you've never seen it before. And I also say, hey, but it's the same anatomy as these MR images. And for these MR images, we have this accompanying example segmentation masks. Well, for a human, it would then be relatively straightforward, perhaps, to find the same structure in the XZ image, even though they've never seen this particular XZ image labeled, and guess accurately the labels for that image. But actually, we can go further. We don't really need that MR data. If we just have these examples of what segmentation should look like, and then unassociated data in some unknown modality, then perhaps we can do something like exploit structural similarities in order to try and learn how we can do this segmentation. In fact, people could, if you show them examples of these segmentation maps and examples of these unknown images, have a pretty good guess at what the segmentation for the images would look like. So that brings us to the description of our particular task. We have a number of example segmentation masks which don't correspond to our data, the data we're trying to segment. So just unrelated segmentation masks. And we want to try and learn a segmenter that's able to take these cardiac images as input and produce the segmentation masks as output. But we don't have any labels, so how do we train this segmenter? Well, one sort of initial idea might be, what about this adversarial training approach? What about if we just say, can we make our segmenter produce realistic-looking segmentations? So we train in this adversarial way our segmenter so that it tries to fool the discriminator, convincing it that it's producing segmentation masks that are looking realistic. And if we just do this, are we able to learn to segment these images? Well, the answer is, we're able to produce realistic segmentation masks, but there's no reason why they should necessarily, in a pixel way, correspond with the underlying anatomy. So as some example, we have some inputs and the corresponding ground truth masks, and the output of our segmentation algorithm, just trained in this adversarial way, they are realistic masks, but they're not corresponding to the input image. There is no correspondence that's necessary. It just has to produce convincing fakes, and so that's what it does. So in some sense, we can imagine perhaps it treats the input as a source of noise, not in the right meaningful way. So what can we do? Well, we propose that perhaps we can encourage some correspondence over and above just this producing of realistic segmentation masks in order to try and produce the correct segmentation masks. So to do that, well, we want to introduce some other auxiliary costs, some high-level costs that are also unsupervised. And I'm going to talk about three that we use in this cardiac setting. But of course, it's somewhat open. So I'm going to talk about input reconstruction, homogeneous region intensity, and region size. So in the current setting, to do reconstruction is not straightforward. There is not enough information in a segmentation mask to be able to reconstruct the input image, because the segmentation mask is just these binary masks. So in order to be able to reconstruct the full image, we add in a residual that comes out of the segmenter as well, which stores something like the background information that isn't in the class of interest, and then they combine by the reconstructor to do the reconstruction. Because of that, we're now able to do reconstruction and use the loss in the loss, just the sort of natural, maybe L1 loss, to help train the network. But also, because we're very interested in keeping our structure aligned, we want the structure of our masks to really be lined up with our input images. We make the reconstructor very simple. In fact, it's very, very simple. It essentially takes the 3-channel mask for the regions of interest and assigns a color and intensity to each of those regions. Then it adds them together. It does the same procedure to the residual, and it adds both of them together to get the final output image. So it's really just coloring in the different channels. Why? Well, then the reconstructor definitely can't move things. It has to reconstruct things, and hopefully that encourages them to be in the right place in the first place. So the way we do it is this film, which essentially is a way of adding and multiplying the channels to get some intensity value. And so when we do this reconstruction cost, we can then train with this error, and you can see some examples that they're not perfect, right? But you can see how we split up into a prediction and residual, and then we produce the reconstruction. And you can see that the reconstruction is sort of a colored version of the prediction and the residual. So another cost is this homogeneous region intensity. In this cardiac data setting, we can observe that, broadly speaking, regions of the same class are of the same intensity. In a very broad sense, if we look at the blood pool here, which corresponds to this mask, it's broadly all this middling colored light gray. And if we slightly offset the mask, then we'd capture a band of the myocardium that's much darker, and that would increase the variance under the region. So if we just try and minimize the variance, then we try and capture regions of a similar intensity. And finally, region size. So it's an observation that you can have realistic masks that are just submasks of real masks. So on the top level, you see real masks. On the bottom level, we remove some parts of those masks, but they still look very realistic. So we just say, hey, make the mask as big as you can. So now some results. So for our data, we use this multimodal whole heart segmentation data set, which has 20 MR and 20 CT cardiac volumes. And they're all from different patients. So when we train for the adversarial setting, we use the images from the MR and the masks from the, say, the CT, which have no correspondence, and vice versa when we're training the other way around. And in particular, we focus on these three common classes, the myocardium and the left and right ventricle. Okay, so here are some results. So essentially, the thing that maybe is worth noticing is that when we include this additional desire to match the correspondence, on top of the drive to produce realistic outputs, we go from MR, the dice scores go from 54 to 66, and for CD from 33 to 51. And just to sort of understand that we can do a lot better if we have a supervised still, as an upper bound, we train a supervised method, and we do noticeably better, but these other results are totally without paired supervision. So let's see a little bit what's actually going on. We do some ablation studies to see which parts of this are really helping. And essentially, we can see that as we add more of the costs, we do better and better until the best results are achieved with all our costs. Okay, so now I'll just quickly talk about some potential extensions of this sort of approach. Thinking about other anatomy, adding labeled examples, or maybe extension to 3D. So this is some very preliminary work, is looking at other anatomy. So now we do some brain segmentation task in the same way. And you can see the input and the ground truth, and we are producing synthetic masks. It's very early on low resolution images just to sort of see whether it's working. But it starts to already be extracting the relevant structure. And in fact, if we just reconstruct from the masks of interest, we get this skull stripping for free. I don't know if you can see. So what about few labeled examples? Well, we haven't tried that with this exact model, but with a similar model that also does this decomposition into the channels of interest and a representation of the residual. We've done some work in our group where we show that using very few labeled images, so just 34, we're still able to retain the performance much better than a fully supervised approach. So we really are benefiting from this semi-supervision, and I'm sure you'll see a lot more of that in this session. And 3D data, well, currently it's 2D, but actually I think that in the 3D setting there might be some advantages. There's this additional structure in the 3D setting where producing a realistic 3D synthetic mask is more difficult, perhaps, than producing a realistic 2D one, such that it will have to rely more heavily on the underlying structure in the input data. So what's going on? Just to quickly finish, this is the high-level idea. We don't have any ground truth data, so we want to do something to train our network, such that later it does minimize the real cost function that we're actually interested in, i.e. the dice. So what do? Well, what about we train this discriminator, and we also train some auxiliary cost functions to encourage correspondence, and then we take that network and we evaluate it on these real the real measure of interest. So that's essentially what we did. But of course, that's some interesting questions come out, right? What should you do to choose your auxiliary cost functions? Here we showed some general ideas, and we applied them to this cardiac data, but there's a lot of flexibility. For example, we do clustering in the intensity space, but you could easily do clustering in the feature space instead if it was the case that the intensity wasn't the right way to cluster. And then similarly, how should you restrict the network? Building in natural equivariance in your network, there was some talk of that earlier in this conference, would be a very useful thing. For example, we know that segmentation masks should be equivariant with translations, rotations, and scalings in the input image. So if we hard code that into the generator network, then perhaps that already is starting to improve the results. So we demonstrate an approach to learning cardiac segmentation without ground truth segmentations, and we show that adversarial approach can be used to do this, but in fact, we also need to somehow solve a correspondence problem, and that can also be approached with unsupervised auxiliary costs. Okay, so thank you very much for having me.
Sorry, before we move to the questions, I have one question. Mats Nielsen, is he in the room, and can he come here and come to Felice? Mats Nielsen, this is somewhat of an urgent thing. Sorry? He left already? Maybe George Cardoso? That's you. Could you come out then? It's mysterious, but it's important. So.
Okay, the paper is open for questions.
I found it very conceptually interesting what you're doing, and what I was wondering is if you have you need to have ground truth segmentations, not necessarily correspondences, but you have to have good segmentations to train the model. And so for me, you always get those segmentations from an image. So can you describe what the situation would be where you have segmentations but you don't have the image?
Yeah, so maybe I can jump back a little bit. Quite a long way. So because of this step where we actually say, hey, we decouple, we don't need segmentations for some real underlying data because we don't use that correspondence, it could at that point come from a shape model. For example, if we had a good shape model of hearts and generated synthetic data like that could be one option. But the other is that because you have this flexibility, if it is coming from data, it doesn't have to be of the same modality, for example. It does open up quite a lot the sorts of sources you can go to for data. But yeah, where you get these from is certainly an interesting thing to think about.
Yes. So can you explain to me what this is more than having a shape model and fitting it to homogeneous regions in your target image? What is it doing extra above that?
Yeah, so I suppose the hope is that the last sort of motivational diagram aims at sort of thinking of what we're really trying to do. So, of course, if you have a good shape model and you know how to fit it to your data, then that is an approach you can take, which of course lots of people have taken. But I suppose what we know, or what seems to be the case, is that the very best results tend to involve this deep network segmentation, at least somewhere in the pipeline, right? So it's certainly the case that you benefit from having underlying shape model, but how should you incorporate that sort of knowledge into the network or into the pipeline? I suppose maybe you could take this as saying, well, one thing you could do is simply do it in an adversarial way, and then not have any supervision, but more have other unsupervised guiding costs to try and solve this correspondence problem. So it definitely is strongly related, but I think it's slightly different.
Other questions? I also have a question. So you touched upon extending this to 3D shortly. When I read your paper, you mentioned that you only do it on the central slices where the organs are visible, and you downsampled 4 times the data. So can you comment on that, if you would do that in 3D?
Yeah. So the reason for downsampling was, well, one, time constraints, but the other was the need to get these generative models to be stable as much. seemingly still much easier if they're lower resolution. But it is the case that to solve these generative models in 3D is difficult, but of course, at the same time, we have lots of advances in generative models. So, for example, making better use of spectral normalization, or doing things to stabilize this adversarial training process, I think should allow us. The only reason we did that was essentially for stability and for time. Yeah.
No more questions? Then let's thank the speaker again.